Okay, let's start. So we have been looking at this fully differential op-amp, and in the last class we saw a bunch of different implementations for this common mode feedback. Again, there are two lines of thought. One is you fix, let us say, the NMOS current and tune the PMOS current, and the other option. In the first thing, the first variant we saw was to directly sense the common mode using two resistors and directly use that to control the current of the PMOS. But here the issue was the common mode was set to some VDD minus VSG of some transistor. So to get a better control on the common mode, we did the following. We estimated the common mode, compared it to a particular reference voltage that you want, and used an op-amp to go and tune the PMOS current source. But the issue with these two techniques was the resistors here, they load your OTA, and that reduces your differential mode gain. So as an alternative, we saw these two. In the first, essentially we instead of connecting the resistor directly, we buffer it and then connect it. In the second, we observed that the although we estimate the common mode in the voltage, this voltage is fed to the OTA, and the OTA converts that voltage to a current. So instead of estimating the common mode in the voltage and then convert to a current, we estimate the average in terms of the current itself, like this, right? And in the other two variants, we saw basically one was the replica bias, wherein you have a replica of this guy and set the voltage to the required common mode. And the second was this. So here the idea was even simpler. You made sure that you had PMOS current is biased to some I0 by 2. In the NMOS side, you make sure that you have a current that is greater than I0. That is something that you can easily ensure. And you know that if this current is not equal to this current, the voltages will change. So we can use this to basically tune the currents here. And the feedback loop will set in such a way that the excess current flowing here will be equal to Ix. Right? And once again here the common mode gets set to VDD minus VSG of this PMOS transistor at the offset current Ix. So yeah, so basically the difference between these two is the following. In these two cases, the output is loaded by a resistor, so that is going to load your DC gain. But the advantage is that it is going to have wider swings, because in these guys the output is directly given to the transistor, so those transistors will in turn limit your output swing. And then we looked at a two-stage Miller OTA. So let me actually refresh it once again so that it's clear. So I'll erase all these. Yeah, so this is your normal two-stage fully differential Miller compensated OTA. So this guy, this RNC is for the compensation in the differential mode. Now again, for each of the two stages, you have to set the common mode. So for the first stage, we'll have a common mode, and here the what kind of common mode detector is good? Is putting a resistor as common mode feedback good? In the first stage, do you think having a resistive common mode detector is good or bad? Yeah, in the first stage it is going to load your thing, and you want maximum gain from the first stage. So among the options we saw, anything besides the resistive common mode detector is good. And in fact the last one that we saw, it's even simpler, wherein you make sure that the current is some I0 plus 2Ix, and then you can basically do this, right? This was the last variant we saw. This is an even simpler thing. And the only consideration here besides choosing the common mode feedback loop is how do you set the common mode reference to? Because as we saw, the common mode or the DC potential here, what does it, I mean, does it set anything else in the system? This DC, it sets the gate to source voltage of these two transistors, which also determines the current. So you can't keep randomly changing this voltage to anything you want. You have to set it to a value so that this transistors carry a particular current. So you have to set to VDD minus VSG of the transistor. So if you want to generate a reference, you can do this. Or if you were to use this CMFB, how do you ensure that this voltage is set to the required value? You make sure that all these guys have the same current densities. So this excess current Ix and this current I3, you know. So you make sure that the VDD minus VSG of this transistor at this current is the required voltage. That's all. Now for the second stage, remember that the swings are going to be very wide, right? And in fact, if as we saw in the last class, if we have a two-stage OTA like this, sorry, where did I go? The output will swing to the full thing, but the first stage, the swing will be limited. It will be reduced by the gain. So if this is Vmax, so this is Vmax by A. And that is why for the first stage common mode feedback, we could directly connect the MOSFET there because we are not limited by swings. But for the second stage, we want to have maximum swings. So we have to use a resistive common mode division. So I'll sense the common mode using two resistors like this. I'll compare it to a required reference using an op amp. And then go and tune this. So a couple of things to note here is that for the first stage, for making the common mode feedback, you can fix, let us say, one of the current sources and tune the other current source. Basically, you can tune either the PMOS current or the NMOS current. Whereas for the second stage, the PMOS current is already set. The only freedom you have is to change the NMOS current. That's the only degree of freedom you have, right? And here once again, if you draw the common mode half circuit, you will find that this forms like a first stage of an OTA. This forms a second stage. So we can quickly draw the common mode half circuit and check it. So I'll quickly draw the common mode half circuit here. So again, if I draw the common mode half circuit, both these guys will come in parallel. Things get shorted. So I'll just remove everything. So we have only one side, something like this, and this connects here. And of course now first stage is not relevant. I'll erase this. So everything, if I draw the incremental half circuit, everything is incrementally shorted. So now this is the common mode half circuit for your second stage CMFB. So here as we see, this forms like a first stage and this feeds to the second stage. So it is once again a two-stage OTA in negative feedback. So this has to be compensated. So we have to put capacitor like this, right? And so which means in the actual circuit, so this is how it should look like in the common mode half circuit. Single capacitor put across, basically this is now 2 times the transistor, right? We have 2 copies of them put together. So in your actual circuit, across each of these transistors, you have to go and put the capacitor. Right? So let's say I call it CCM by 2. Right? And as usual, again, if you have a parasitic capacitor here degrading your phase margin, you can go and put a parallel cap here. Do this. And the typical value for this reference voltage for your second stage is half the supply, because this is the final output. You want it to swing equally on positive and the negative side, so you choose it to be at mid supply. And other thing was here this guy, as we saw, we can either have an NMOS input pair 5 transistor OTA or a PMOS input pair 5 transistor OTA, but the output here is going and connecting to an NMOS. So this should be an NMOS or a PMOS input. It's a PMOS input because again, if I draw the circuit, it becomes clear. If you have a PMOS input pair 5 transistor OTA, so we'll have something like this. So this is the plus side, minus side. The output here is going to a second stage, which is an NMOS transistor. So having a PMOS input pair is good because then the bias voltage is at a reasonable level. And once again here, you have to make sure that all these guys have the same current densities, right? Only then you will not have any systematic offset at the input. Okay. So this will be a PMOS input pair OTA, and you also make sure that the NMOS transistors, all of these NMOS transistors here have the same current density. Okay. So this is the common mode feedback. Again, let's do the differential mode half circuit. We did it in a hurry in the last class. Let's do it once. This is okay, common mode feedback, fine. So let's see, yeah. So let's now draw the differential mode half circuit. So I'll erase all the unnecessary stuff. All the circles is not needed. So here again, for the differential mode half circuit, I assume that we have a differential input like this, say VID by 2 and minus VID by 2. So which means all the node potentials along the line of symmetry, they'll all be incrementally 0. So this is ground, this is ground, this is ground. So basically this is also ground, right? And even this small signal ground. So this OTA, both the inputs and the outputs, they are at incremental short. So it's not relevant at all. I'll remove the OTA. And of course now I can take only one half of this. I'll delete this half. So this gate is incrementally short. Oops, I had a resistor here, sorry. Okay, so this gate is at incremental short, and this is also incremental short. So from this node you have this capacitor to ground, and both this R and C connected to ground, so that we can simplify like this. So I'll incrementally short this. I'll have the Miller compensation capacitor for the CMFB2. Sorry, this is not. This is the common mode sensing resistor. This is, let us say, the Miller compensation capacitor for CMFB. This is the one that you're adding for the 0. So similarly for the first stage, this is incremental short. So this all goes away. And same is the case with this gate. So here everything goes off. So this is incremental short. So basically this just adds a capacitor, nothing else. So whatever common mode feedback you have for the first stage, that is going to add a capacitive load. So that capacitance you add it here, okay? And supply is incremental short. That's it. Okay. This is what we'll have. And of course on top of it you will have your final load conductance and load capacitance and stuff. Right? So this is basically your plain old two-stage OTA that we saw at a block level. Just that both the OTAs are single-ended input, single-ended output. Because we are drawing the half circuit. So we'll just have, let us say, plus GM1. We have some G1 and C1. Sorry, it's not plus GM because everything is inverting. So let us say it minus GM1 minus GM2. I have an effective GL prime and CL prime. Make some space here. And again we have CC and RC, which is for compensating the differential mode thing, right? So the only thing I want to highlight is here this should include your CMFB load also. Similarly, GL prime and CL prime will also include the load from CMFB2. Okay. So when you are finally designing for your differential mode loop, for that loop to have a particular phase margin and omega u, the load from your CMFB must also be taken into account. Okay.